So the answer is the first three are all good reasons to focus on how time scales with input size rather than absolute time. So the first reason is if we have an understanding of how the time depends on the input size, well, then we can predict how long it will take before we actually execute a program. If we have to run the program to figure out how long it takes, well, that's not going to be very useful because we've actually finished it. We've got the result we want. If we only learn how long it takes on that particular input, we haven't learned anything useful to figure out what it will cost to run it on some other input. So we want to be able to make predictions by understanding how the running time depends on the actual size of the input. The second reason is also true. By understanding how time scales with input size, we get a better idea of how the cost will change over time. Computers keep getting cheaper and faster. This was observed by Gordon Moore in 1965 and turned into the notion that we sometimes call Moore's law today. It's not a law in the sense of a physical law, but it's a law in the sense that the history of computing has followed this trend where the amount of computing power you get for the same cost approximately doubles every 18 months. So what you can get for $1,000 today is half what you'll be able to get for $1,000 a year and a half from now. That's a pretty nice property to have, but it means that understanding the cost of something today doesn't tell us very much. What we really want to understand is the cost in a more fundamental way. The third reason is also true, that by understanding how time scales with input size, we get a much better fundamental understanding of our algorithms than if we just had some absolute time measurements for a few different inputs. The fourth answer is not correct. Abstract answers can be just as wrong as concrete answers, but having good abstract answers will allow us to understand things much more deeply than a few specific concrete answers will.